Okay, this problem is 11.49. It's a momentum problem. Oops, not 46, 49. We have a bullet. So the picture is that you have a bullet shot towards a block that's at rest. So ultimately, the thing that we're trying to find is this initial velocity v bullet. And I'd write it out because there's a block and it might confuse folks. So mass little m, block, or the bullet has mass little m, block has mass big M. And then what happens, of course, that almost instantaneously, not instantaneously, but in a change in position that's nearly immeasurable, the mass and the bullet stick together, right? The bullet embeds itself. Right now it's sort of stuck in there. And now the system is moving as one with the speed v, and then it slides across a horizontal surface and then comes to rest. So this is a type of problem where momentum, so you got to be careful with the subscripts here because you have an inelastic collision here and you use that inelastic collision to do a kinematics problem. But the problem is we're given the kinematics problem and we have to work backwards, like a lot of these momentum problems go. So that's a distance d, toss a coefficient of mu on the road or the surface. There's YouTube videos out there where they actually do stuff like this, where they can test the speed of a bullet that's fired out of like a rifle or something by shooting it up into a block, and then like the block shoots up into the air. Really, really neat stuff. Let's do the problem though. So we're going to have to use kinematics to find this speed of the block after the collision, and then work backwards, because if we were to just do this problems first or in the direct order, it would be the initial mass of the bullet times the initial velocity of the bullet. That's going to equal the mass of the bullet plus the mass of the object times that, what we might call like initial velocity for the kinematics problem. You can define whatever symbols you want, but you have to be careful that you don't confuse the initials and the finals. That's why to be completely honest, we'd probably denote this as like V0 and make this speed V1 to make, instead of an I, just make it a 1 and then make the final velocity a 2. That's probably the best way to do it. That's why we do the 0s and 1s and 2s rather than initials and finals. But so yeah, this will be V1. So you would do, if you knew the initial velocity of the bullet, you do this problem, divide by the sum of the masses to get the launch velocity, or the V sub 1, and then do kinematics to figure out the distance, which would be like V2 squared equals V1 squared plus 2a times d. And like from Newton's laws, you know that the acceleration is coefficient times g. I'll just let you verify that for yourself. But you have to work backwards now. You know d, and so you have to find, and you know that V2 is 0, so you have to find V1, and then plug that into the top part to find the initial velocity. So we've got, let me just check my time here. We've still got 8 minutes or so. So yeah, and then in the homework problem, there's some masses here. So V1, then solving for that, V1 should be square root of 2 mu g times d. Okay. Hopefully you can resolve all these minus signs, because the acceleration, so if you define the coordinate system that is positive to the right, then initial velocity is positive, V2 is negative, A is negative, D is positive, and so the negatives should all cancel out. So that is the expression for the velocity after collision, before it slides a distance d. But then, so you plug that into the final part of the momentum thing. And then it looks to me like you can just divide by the mass of the bullet to get the final result. And so it looks to me like the final speed, or the final result, which is the initial speed of the bullet, then is, I'll write it. Yeah, I have enough room. I'll write it m plus big M over little m times square root of 2 mu g times d. Oftentimes in the parentheses like that, instead of writing m plus big M over little m, we'll just write 1 plus big M over little m. And in that way, we actually don't need to know the actual masses. Sometimes all you know are the ratio of the masses. In the part B of the problem, you're definitely given, in part B of the problem, you're definitely given the masses of both of them, but there may be problems, down the road where you're only given the ratio of the masses. So that is how you solve it algebraically for part A. For part D, you're just plugging in numbers.